going to have charges. We're going to have particles that are electrically charged, and what we're going to need in the end is the type of charge. In an electric field, do you remember the direction in which a negative charge has? I mean, the electric field in a negative charge has?
Attraction.
More than attraction, here it has a different name, a different word. The word is toward. Okay? So in negative particles, in negative charges, um, this charge is like trying to absorb the electric field that is surrounding it. Okay? Did you watch the videos that I posted on Classroom about the experiments on how to see the electric field? Okay. So when you have a negative charge, the electric field goes in the charge, towards the charge. But when you have a positive charge, it's like from the internal of the charge, the electric field is going outwards. And that's important because it goes in every direction, but it goes outwards. Now, from this, we're going to apply this principle that in negative, the field goes in, and in positive, it goes out. Okay, so that's the main difference between the two kind of charges. And as you can see, they go in different directions. Okay, they go in different directions everywhere. It's not like we can say that there are 7 electric fields. No, there are infinite electric fields because it's a region. Okay, so the region is everything that is in the surrounding area. But the intensity is going to depend on how close is it to the charge. Now, take a look to the example that we're going to be working on today. The idea is that with this exercise, you should be able to get the resultant of the electric field, but in the point P. So we do the same then in the in the superposition principle. Okay, so take a look. In the negative charge, the the electric field is coming toward the particle, like this, in every way. Okay. Now, what direction is this field going to have according to the point P? Take a look. What arrow from all the arrows that I draw, from all of them, what arrow is going to pass through the point P? What arrow is going to have the same direction? Exactly, this one. This one right here. So, this arrow, I will copy it like this, and I will extend it until I touch the point P. This is going to be my electric field due to the last particle. Okay, so I'm gonna call each particle with a letter. This is going to be my particle A, A1, B1. No, I'm just gonna call them with letter A, B, C, and D. Okay, better like that. So this is going to be my electric field due to the force D. Okay, it goes in this direction because remember that it goes inward. Now I will analyze this one right here. Because it's positive, all my arrows are going to go outward. That means that my arrows are going to look like this. Now, which one of all these arrows is going to pass through the point P?
The one that is down.
This one that this one that is down, okay? So I will project the arrow, I will extend the arrow. And here I'm going to have my electric field due to the charge B. So this is going to be EB. Now I will analyze the arrow A. Because it's negative, the arrows go toward the particle in this direction. What arrow is the one that passes through the point P? Exactly. Yes, thank you. So this arrow, I will extend it more or less like that. Okay, that's the projection of the arrow, and I will call this electric field A, and now I will get rid of the other arrows. Okay? And in the last part, I have my charge C, okay, which is positive. If it's positive, all my arrows go outward. Now, what arrow is the one that is going to pass through the point P? Exactly. Thank you so much. What you are doing in this moment, you're making me happy. Okay? You minor and left, you are making my day in this moment because you are participating. I know I didn't mention Ashley. Actually, you participate all the time. You always make me happy. But I feel proud because I see that you are getting the point. Okay? That's nice. That's nice. So we can go on. We can extend this arrow until it reaches the point P. And I'm going to call this electric field due to the charge C. Now, I will work only with this. I will work only with this. Okay? So, what do I need? I need this angle right here. I need it because I will need to get the components of the electric field A. Okay? Because that's the only arrow that has components. So I'm gonna need the distance, okay? This distance, and I'm going to need the angle. So right now, in this moment, I am going to call this force, this distance A. Distance A is going to be equal to, because I don't have that distance, I know I can use the hypotenuse equation. So I say that this is equal to 0.5 to the second power plus 0.4 to the second power. How much is this? How much is this?
0.6.
0.6.
0.64 rounded meters. Okay. Now, I'm going to write the rest of the information I need. I also need my angle, so I'm going to get my angle. So my angle for the electric field A is going to be equal to arctangent of, if my angle is here, okay, my opposite side is 0.5 and my adjacent is 0.4, okay? So my opposite, which is 0.5 meters, divided by 0.4 meters, and I get this angle.
51.34.
Okay. Now, the rest of the information is given in the problem. I mean the distance for the electric field B. The distance B is going to be, okay, this is my electric field B, so this one is coming from here, and the distance B is equal to 0.5 meters. What is the distance C? What is the distance C?
0.4 meters.
What is the distance D?
0.5 meters.
Okay, and this is how I organize the data. This helps me a lot, but unbelievable, okay? It is amazing if you organize the data this way. Now from this, I will proceed to calculate each electric field, okay? So I'm gonna get the electric field in A, B, C, and D, okay? And I will get the electric field. How do you see the screen? Is that okay? Do you read?
Yes.
Okay, that's good. So here I'm going to have my electric field A, electric field B, C, and D, and I copy the equation. For each, I will use Kc times the charge A divided by the distance A to the second power. For B, is Kc times B divided by the distance B raised to the second power. For C is almost the same equation. So that's why I'm telling you, try to work as organized as you can, because the procedure looks a lot easier when you work very organized. And in the last one, you're going to have Kc times the particle d divided by the distance d raised to the second power. We're going to substitute by the givens. The way I write the charges, for example, the charge A, as you can see, is 4 microcoulombs. To do it faster, I don't do this, okay? I don't do this. In my procedure, the one I do, to work faster, I just write the 4 and the exponential here. That helps me to work faster, but it is incorrect because they are different things. It's not the same. But if in your calculator you use the scientific notation button, you're gonna be just fine. Now, I don't like to work like this in class, but I'm just telling you a tip for if you want to save time during a quiz, for example. Okay, distance A raised to the second power is 0.64 meters to the second power. Voila. And you know the lazy teacher is going to copy and paste as usual. I'm just going to do every single change that I need, okay? So in this one, the particle B has a charge of 8 microcoulombs. And the distance between them is 0.5 meters. The number 3, my charge is not 4, is 6 microcoulombs. And the distance between the charges is not 0.64, it is 0.4 meters. In the last one, instead of 4, I have a charge of 5 microcoulombs, and the distance between them is 0.5. If I work like this, I work faster. Now, you can skip it, but in the end, you're going to be working more than needed. How much do you get in the first one?
87,768.55.
87,768.55.
56 rounded.
56 rounded. Now, remember the units? For the electric field, the units are Newton over Coulomb, or Newton per Coulomb. Okay, what do you get in the number 2?
287,600.
What do you get in the 3?
337,031.25.
And in the last one, how much you got?
$179,750.
Please don't forget to write the units. That's important. So you have the values of your electric fields. So I'm going to take my particle, I'm going to make it bigger because I'm going to work in it. And I'm just going to include all the information from here. So in A, I have the value of 87,768.56. Okay. In C is in D is, I know that you really don't need to write it like this, but I like it because it gives me a visual information that is priceless. Okay. In this way, if you have the information well written, it's gonna be easier to locate this information in the table of components. And the angle that we got was 51.34 degrees. Now, this is your prior sketch, okay? And with this, we're gonna use the table of components to get the resultant. A ver. Well, so here in the vectors, I'm going to locate the 4 vectors that I have. I have vector A, B, C, and D. I have nothing in E, so I'm going to basically ignore this row. My first vector A is this one, and it has the angle. So I'm gonna put it here. I know that it's the one with the angle. So I'm gonna get the components. My X component is guys, don't forget this because I noticed that you forgot. Okay? Don't forget this, the direction at which it is going. This vector is going to the left and up. Okay? So left and up. Because it goes to the left, it's going to be negative for x. Okay? And the way we get the component is the value of the vector A, which is 87,768.56 cosine of 51.34. My dog, sorry. Sorry about it. I get the component in x, but also in y. Remember, it goes to the left, so it's going to be negative in x, but it goes up, so it's going to be positive in y.
Negative 54,828.81.
Sorry, I was checking. 54, 828.81 Newton over Coulomb, and the one positive gives me 68,535.54 Newton over Coulomb. I finished the first vector, I go with the second vector. Take a look. The vector, where the vector is located, but where the vector is going. The vector is located up, okay? It's located above, but the direction of the vector is down. This is what really matters. So my vector, it's coming down, is my vector B, and this one measures 287,600 Newton over Coulomb. So this one does not have X component, so you can ignore it, but the Y component, because it's going down, it's going to be negative. Negative 287,600 Newton over Coulomb. My vector C, even though it is located in the left, the arrow is pointing to the right. So this vector is going in this direction, is my vector C, and it measures this value. Because it's just moving in X, it's not going to have a vertical component. And because it's going to the right, it's going to be a positive value of 337,031.25 Newton per Coulomb. And the vector D, as you can see, is also going to the right, and it has this value. So my vector D is also in this direction, and it measures this, Newton over Coulomb. Now, it's just moving horizontally, which means not moving vertically. So the vertical component can be totally ignored. And because it goes to the right, it will be positive. Now we're gonna get the results, okay? We're gonna get the sum of the x component and the sum of the y component. How much did you get in x?
461,952.44.
And how much did you get in y?
Negative 200, 2,1964.46.
Thank you. And now comes the easy part, that is where we need to get the resultant. I'm not going to write the equation, you already know it. I'm just going to write, not the answer, I'm going to do the procedure. How much did you get?
511,262.45.
This value is greater than x and also greater than y, so at least it makes sense. And then the angle. As you can see, this procedure, guys, is the same procedure that we have been doing. The only difference is how the electric field goes, how it behaves according to the sign of each of the charges, and also changes the formula. But the rest of the procedure is the same that we did before. We can cancel the newtons per coulomb. How much did you get?
Negative 25.37.
Okay. And if I say, okay, that's it, But if I say, I want you to sketch the resultant. So you have this. You have your x to be 461,952.44. And you have y that is 219,064 point whatever. Okay. So what you can do is you can say that you can use work only with these digits. Okay. You can say that this is approximately equal to 4.6 centimeter and that y is approximately equal to 2.2 centimeters. All I did was divided by 100,000 just to make sure. And with this, you can easily sketch the resultant. I don't know, I'm not gonna have the time to do it, but and also in the quiz, I'm not going to ask you to do it in a quiz, but just in a homework, for example. So that is my Cartesian plane. I'm going to focus on the signs. This one is negative. So positive for x, negative for y refers to this quadrant. And 4.6 in x is going to be between 4 and 5, more or less here. And in y, it says negative 2.2. So it's going to be negative 1, 2, more or less here. And the resultant will be from the origin to the opposite corner. And the angle will be here.